Hello, and thank you for joining us. Today's webinar is Choosing Your GC Column, Part 1, Purge and Trap Volatiles. Our presenters today are Amy Nutter, VOC Applications Chemist from Teledyne Tekmar, and later Chris English from ResTech will join us. We will be taking questions, so please feel free to submit your questions throughout, and we'll address them at the end of the presentation. This webinar is being recorded and will be available within a few days. Now I'm going to turn it over to our first presenter, Amy Nutter.
Thank you for the introduction. I'm Amy Nutter, Applications Chemist here at Teledyne Tekmar, and today is part 1 of our GC column selection webinar series with Chris English, the Laboratory Manager at ResTech Corporation. He will give us an overview of chromatographic separation and how to choose the correct column for your purge and trap volatiles analysis. I will cover a quick overview of the purge and trap technique in our products. And then Chris will give you an overview of chromatographic separation, typical column phases, GC figurations, and film thicknesses. And then he will get into some method development and translation, and then he'll tie it all together at the end, and then we will have time for some questions. Now let's get into how purge and trap works. The theory of purging and sweeping the sample with an inert gas, called dynamic headspace theory, sounds simple, but it's a very complex process. Purging a sample to extract analytes is a gas extraction. In purging a sample, the system is no longer at equilibrium. This is because the VOCs that move into the gaseous phase are constantly being removed by the purge gas. Continuously replacing that headspace causes a disequilibrium, in that there's always a higher concentration of VOCs in the liquid phase than in the gaseous phase, creating a net movement of VOCs from liquid to gas, extracting the VOCs from the sample more efficiently and improving on sensitivity. Then the gas is swept away onto the trap, where it is then concentrated and released to the GC. A basic purge and trap consists of 5 main parts: the sparger, flow control, 6-port valve, analytical trap, and heated transfer line. The sparger is the glassware on the front of the instrument that receives the liquid sample to be purged. Purging that sample extracts the VOCs by dispersing inert gas through the sample matrix for a preset time and flow. This flow is controlled by a mass flow controller or a pressure regulator that monitors and precisely controls the gas flows throughout the entire purge and trap process. From there, the 6-port valve directs the gas containing the analytes to the analytical trap for concentration. By back-flushing carrier gas through the analytical trap, the 6-port valve directs the VOCs to the GC for separation and detection. The analytical trap is used to capture and release VOCs swept out of the sample by the purge gas. Trapping the VOCs helps create a smaller band of analytes traveling to the GC column, producing greater signal-to-noise ratios and lower area-to-height ratios, generating sharper peaks and better sensitivity and resolution. Once the VOCs are captured, the trap is heated, causing the VOCs to desorb. Carrier gas is used to desorb VOCs off the analytical trap and carry them through the heated transfer line to the GC. Teledyne Tekmar is the market leader for purge and traps in the US, and we offer several different options. The Lumen Purge and Trap Concentrator, shown on the right, is our standalone waters-only concentrator that can be paired with the Aquatech LVA autosampler. We also have the combined autosampler and purge and trap concentrator, the Atomics XYZ, shown on the left, capable of analyzing soils, solids, and water samples. So now that we've covered what happens to the sample before it gets to the GC, let's get into how the analytes are separated for detection. Our guest speaker today is Chris English, who is the Laboratory Manager at ResTech Corporation. He has managed a team of chemists in ResTech's Innovation Laboratory since 2004. Before taking the reins of the laboratory, he spent 7 years as an environmental chemist and was critical to the development of ResTech's current line of volatile GC columns. It is a pleasure to have you for this series, so go ahead and take it away.
All right, thanks a lot, Amy. I appreciate it. I think one of the most critical parts of having good chromatography, whether it's purge and trap or any other type of concentration technique, is the chromatographic separation. And the idea behind the chromatographic separation is getting those analytes focused at the head of the column. Once they're focused at the head of the column, they begin to partition in and out of that stationary phase and move down the length of the column as temperature increases. And that's really the mechanism behind chromatography. So it's really as simple as that. Now, one thing to keep in mind is the longer the column, the more effective plates. When we say effective plates, we're talking about that partitioning in and out of the stationary phase. And that gives us our separation mechanism. However, if the analytes spend too much time in the stationary phase, those peaks begin to broaden. And so we start to lose some of that advantage of using those plates. So therefore, we really want to find the shortest possible column that can perform the separation that we're looking for. And that's where selectivity comes in. And so when we think about different columns, selectivity is the most critical of those components that we're looking for. So we look at different stationary phases. These are some examples. On the left is a cyanophenyl polydimethylsiloxane stationary phase. That's similar to, or that's the composition of a 1701 or a 624, depending upon the percentage of the cyanophenyl. On the right-hand side, we see a diphenyl. Diphenyl can be a 5-type phase or a 35-type phase or a 20. It's all different percentages of that diphenyl. So common volatile columns would be around 20%. Now, this is a stick and ball diagram of what a diphenyl phase would look like. And the reality of it is, I think of these as big, long, straight polymers, but the reality is it's like a ball of string. Like it's this big, long strings that are all tangled together. And when they are tangled together, sometimes they break. And that's what we see as column bleed. So it's pretty interesting. In this case, we've got our PDMS, our polydimethylsiloxane. So that's a 1-type phase, dimethyl, and we'll show the functionality or the composition of that. And then also we've got our phenyl phases that we talked about, whether it's a 502, which is a ResTech, or a VOC, which is a Sapelco, an Agilent, and then a Vocal, which is a Sapelco. And then the manufacturers all have different types of the 624 phase. We talk about the VF type or the 624 SIL, which is where we've actually put phenyl in the backbone to stabilize that backbone, like we talked about with the thread, a ball of thread, where we can keep that polymer straighter. And if we can keep it straighter, it doesn't interact with itself and break down. Then there's some specialty phases out there like the VRX, which is specifically formulated to separate some of the older methods like the 502.2 type method and get those analytes separated. So it's a tuned stationary phase. And the same thing with the VMS. The VMS stands for volatile mass spec, and that was designed to basically resolve compounds that have interfering quantification ions with each other by mass spec. Now, if we look at a 1-type phase, anytime we talk about phases, if I talk about a percentage of a substituted phase, that is like a diphenyl, like is 5% diphenyl, that 95% is dimethyl. And so this is our simplest phase, and it is quite useful for a whole variety of different things, but it's certainly its selectivity has not been tuned specific to volatiles or any other types of compounds, although it's got an outstanding maximum temperature. And then here are all the phenyl phases. The thing that we look at with phenyl phases when we're looking for volatiles is the separation of bromomethane and also the elution of methanol and water at the front end. One thing to keep in mind is if you can adjust where the water and methanol come out, you can diminish the amount of the effects on the linearity for those gases at the front end. So these phases all kind of suffer from the fact that that water methanol elutes right around the bromomethane and interferes with that analyte. On the other hand, it is a bomb-proof type stationary phase, and that is This has been used by some manufacturers like SRI with air as a carrier gas. So they're using air at 180 degrees with a 502.2 type column, and it's got good lifetime and it runs just fine. So that's one of the advantages. You certainly could not do that with a cyanotype phase, like a 1701 or 1301 or 624. The difference between a 624 and a 1301 is simply the column dimension. The thin film columns are considered 1301, and the thick film volatile columns are considered 624. That naming goes back many, many years, and that's a seminar in and of itself. Those are substituted 6%. So the 624 and 1301 are 6% cyanophenol, and then the 1701 is about 14%. So it's twice the functionality. And so that makes it more retentive for halogenated volatile compounds, the 1701. So sometimes that is an appropriate phase for looking at a smaller list of volatile organics. And here's the 624 SIL-MS. The thing that the advantage this gives you is that maximum temp of 320 degrees, whereas other columns will only go up to about 280 degrees on a thick film volatile type columns. Now, this is a real novel phase because it's got a high maximum temperature, but it's fluorinated. So you have this large electron cloud around those fluorines that is excellent for electronegative type compounds and lone pair species. So anything that's halogenated does very well with this stationary phase. So this is another good candidate. The reason people don't use it for US EPA methods is it doesn't just have one coelution of gases, it has two coelutions of the gases at the front end. So the gas resolution is not good at all. And the retention of freons for those particular gases up front is not good. So for GC configurations, generally we're going to use the large bore columns for an FID because it's a mass dependent detector, or PIDs. So really the more we can get to that detector, the better sensitivity we have. And therefore we use columns like a 5.3 or 4.45 millimeter internal diameter. On the narrow bore side of things, 0.18 millimeter ID and the 0.25 millimeter ID is kind of the sweet spot for volatiles. You can have appropriate splits, so you have good sensitivity, yet you have a very rapid transfer from the trap onto the column because you can do a 20 to 1, 50 to 1. So that means if you're doing a 50 to 1 split, it means you have 50 mils a minute running over your trap. And that's going to minimize any dead volume and allow for a very efficient transfer of those volatile organics from the trap to the head of the column. And that's what makes for good chromatography. So we do highly recommend the 0.18 to 0.25. A lot of people are like, well, I think I'm gonna up it to the 0.10 and get even better chromatography. And the problem with that is the water and methanol that are generated from purge and trap can cause problems at the front end. So you can have interferences of gases. And then in addition to that, it's the linear dynamic range that also suffers. So a 0.1 column is going to saturate very quickly. And that is we have fronting and distorted peaks throughout the chromatogram because we're putting too much on that column. And so it makes a lot more sense to have something like a 0.25 or 0.18 millimeter ID where we can have a large calibration curve and not have to keep diluting samples again and again to get them within our calibration range. So for film thickness comparisons, here's a really interesting example that we had from one of our vendors years ago that sent us pentane that was 99% pure, but we couldn't coat columns with it for some reason. As we put these polymers into a solution like pentane, and then we basically put the pentane in the columns and pull vacuum and slowly draw the pentane off, and that leaves the coat or the coating or the stationary phase behind onto the columns. So we had issues with that. We ended up testing it and finding that it was only about 85% pentane. The rest were pentane isomers and a variety of other contaminants that were at the front end. And it's now interesting because we, many times for our products, we send our vendors the test that we want that we want our product to be tested on. And so like O-rings and septa and our solvents that are coming in, we develop the test and send it to our vendor, and then it meets that purity, in relation specific to our test. So if we're going to develop a new method, the first thing to do is go out on the internet and see what you can find. You might find the perfect chromatogram. And in this case, we have a chromatogram that's run for US EPA 8260. It's on a 40 meter, 0.18 millimeter by 1.0 diameter film thickness. And the reality is we could probably do this analysis faster if we used a 20 meter, 0.18 millimeter with a 1.0 diameter film thickness. And we know that we can't just switch the column and put another column in there with these conditions because the chromatography would look terrible. On the other hand, we have no idea how we could come up with conditions that would be amenable to this different column dimension. Now, the same goes if we wanted to switch to a 30 meter, 0.25 millimeter by 1.4 diameter film thickness column. We're left in the same dilemma. So that's really an issue for labs that want to switch and they want to optimize and come up with faster runs. And so we have a method translator that allows you to do that type of translation and move from one column format to another. Now, if you go on the website, you can click on Resources Education, and then down below it's EasyGC Method Translator and Flow Calculator. At a later date, we'll talk about the Pro EasyGC Chromatogram Modeler. That's where you just enter in a list of compounds and you'll get column recommendations. But in this part one, we're going to look at different configurations and moving from one platform to another. So some concerns here. If we're starting out with, let's say we're starting out with a 502.2 column and we do have a bromomethane issue, this is not going to help you out. Like you can translate to another column and you're still going to have a bromomethane issue. And so having the correct phase to start out with is the most important thing. Just like we talked about, it's called the alpha factor, which is the selectivity factor, is the most powerful term that we have in resolution, is having the right selectivity. So picking the right stationary phase to begin with is pretty important. The other thing I get is, I'll have this in tech service where customers call, they have a competitor call, and they're like, I really need to get a Restech column in here so I can, fix my tailing. I'm like, yeah, it's not, chances are very good it's not the column. It's probably a leak. It might be insertion distance. It could be a variety of other things. Let's fix the problem on your current column. So there's a good chance you might not need a column and you can continue to run with that particular column, especially in volatiles, because columns last a very long time, unless they're exposed to oxygen or water at high temperatures. Water at low temperatures is not going to cause any problem. And so that's what we have when we're desorbing and water condenses at the column. By the time it's out of the column, it has not gone up to temperature. Because you'll see that when we talk about elution temperature, the elution temperature of the water is still down in 30 or 40 degrees. So, and then can I run different methods on the same column? Certainly you can run different methods, just depending upon how you're set up and what methods you're going to run, but they should be amenable to, it should be volatile type organics, whether that's gases or whether it's the MTBE and things like that, or alcohols. And then of course we've got a method that works and we want to improve it or migrate it over without doing an extensive redevelopment. And that's where our method translation comes in. So, and then what kind of method changes can we do? Of course, we can change our platform. So that involves the length, smaller ID. We can look at different film thicknesses. We can also look at different carrier gases. And I know there's a big move right now to evaluate different carrier gases because of the helium shortage. And this is a great opportunity to take a look at that and do that translation. The other thing is, if we were going to move from an FID to a mass spec, we're now going to go from atmospheric to vacuum. And that will make a change for some of your later eluting compounds, change in retention. So in any one of those combinations. So when we do our method translation, our goal is to have the same elution order and a similar resolution. Now, we're not going to promise the exact same resolution because if you cut your column in half, you now have 50% less effective plates, and you lose about 40% of your resolution by chopping the column in half. So, and when we talk about that in the inverse, we're telling customers, don't go from a 30 to 60 meter column unless you can really justify it, because from going from a 30 to a 60 meter column, it's only going to increase resolution by about 40%. And that may not be worth double the price of a column. So, and of course, how does it do it? What's the math behind that? Bloomberg, and there's a whole variety of people that have written books on thermodynamic modeling that would describe this in more detail. But suffice it to say, our goal is to maintain that same elution temperature. And this is a good example of that. If we look at this, this is what our program is designed to do. So those compounds that you have the dotted green line, they're going to be, regardless of what column platform we look at, they're going to come out at 174 degrees for the last compound, and the middle compound at 126 and at 65. It's interesting because when we were developing the VMS column, we had a cluster of 7 compounds in the front, which included chloroform and 2,2-dichloropropane and a bunch of different compounds, cis-1,2-DCE. And we realized that the elution temperature of that was critical to getting them separated. And then it was critical to when we looked at other platforms. And this was kind of before the method translator, for us came out. So it's just kind of interesting that we had kind of fallen backwards into this same conclusion, right? So here's our maintaining our same elution temperature. But in order to do that, we're not only changing the flow, but we're also changing the temperature. Here's a good example of a 20 meter, 0.18 millimeter, 1.0, and we look at a translation between the two. Now you could go whichever direction, right? If you had the 30 meter 2.5, 1.4 film thickness column, you could translate it to a 20 meter 1.8, and the reverse is also true. What you'll find here too is, look at the difference in runtime. So we can get a 14-minute run on the 20 meter 0.18 millimeter column versus a 21 or 22-minute on the 30 meter 2.5. So there is a significant increase in your runtime. The one limitation you may find here is if you're going, like if you go down to a narrow bore, you'll notice the ramp rate increases. And with a 100 micron column, that's the 0.1 micron or 0.1 millimeter, which is a 100 micron column, you're going to see you can come up with ramp rates that may not be possible with your instrument. So that's one thing to keep an eye out for. So here's our EasyGC method translator on the left. We also have a flow calculator. That's a whole different topic. But if we take a look at this is how we're going to fill it out. So we have our original on the left-hand side, our translation on the right-hand side, and we're going to enter our column parameters. What's the column we have on the left-hand side, and what's the column we want on the right-hand side? We can then enter our control parameters. If you see the blue arrow, that would be your set point, but you can move that blue arrow wherever you want. So if you want to set it for average linear velocity, or you want to set it for hold-up time, which is dead time, you can adjust that, or many people just use flow. So that's very common. So, and then oven program, we enter in our current oven program, and that will, the blue on the right-hand side will translate for you. So of course, whether you have constant flow or constant linear velocity or constant pressure, those are all options on there as well. And then we can click our translate. If you look all the way down at the bottom, you'll see the increase or decrease in runtime. In this case, it's going to be 0.64 times faster. So that means it's slower, right? If it was 2.0, you'd be 2.0 faster. So we went from 14 minutes to 21.9 minutes. And that will give you the same elution. Those two columns have similar plate characteristics, so your chromatography is going to look very similar as well. So we can do that translation. We can also, down at the bottom for results, we can click on speed, and it's going to try to pick up speed if it's all possible on there without compromising your elution order. And then efficiency also, if there are opportunities where it can get better efficiency. And some of the things it's going to look at are like the Van Diemter curve, and that is optimum linear velocity. So if you entered in values where your flow is higher than the optimum linear velocity, by clicking on efficiency, it may find a better efficiency. So you could actually pick up some resolution that way. So, and then of course, custom, we just allow the customer to do whatever they want. You know, that's one of our options. You can go out there and just play with it and enter in whatever you want. So now's the opportunity to show some real life examples, so we get a chance to see like what it really looks like. And I know we've had a lot of calls in tech service where customers are running semi-volatiles and they're clipping their column constantly. And they call in and they say, I need a new column. I'm at 28.5 meters long and my resolution's no longer any good. And the big question is, did you adjust your flows for a 28-meter column? Because you used to have a 31-meter column and now you have a 28-meter column. No, that won't, I mean, I don't know why I would need to do that, you know, and the reality is your flows are too high. So if you do a method translation for a 28.5-meter column, you're going to find out it looks pretty much the same as a 30-meter column because the differences between the two are very little. However, if you just set your column up and clip a big chunk of it off without adjusting your pressure, you will have issues with resolution. So here's a good example of an original. So our original column is 30 meters, 0.25 millimeter by 0.25 micron film thickness. And then we have, so what we did was in the middle where it says original method, all we did was chop it in half and find out and see what happens, right? And of course you see the resolution between peaks 4 and 5 collapse. And now when we go back and we translate the method from a 30 meter to a 15 meter, we find that we've actually picked up some of that resolution. Now, the reality is you've lost 50% of your plates. So you essentially lost 40% of your resolution, but yet you didn't lose 60 or 70% like we saw here with an untranslated method. So another example here of some compounds on a 30 meter 2525 again. Another set, and you can see the original method where we've got, what, 50% maybe? And on a translated, we're 70, maybe 75% resolved. So it does make a difference. Now, if you're dealing with a whole variety of different compounds, this is going to make a big difference throughout your chromatogram. And getting those separations is important. So pulling it all together, choosing your volatiles column, you want to find, first of all, finding the right phase, because remember, selectivity is the most important part of the job of finding the right column. So, and again, don't be afraid to call tech service, check out the internet, you know, do your research. And understanding just the basics of stationary phases will go a long way. So understanding that like dissolves like, so if we have phases that look a lot like the compounds that we're analyzing, like for instance an RTX 200, and we're looking at a bunch of chlorinated solvents, that may be an appropriate stationary phase. And then also optimizing those column configurations. We want the longest possible column without compromising our efficiency and getting that band broadening that occurs. So in many cases, a 20 meter 0.18 is perfectly appropriate, as well as a 30 meter 2.5. With volatile analysis, we do have to stick with a specific beta, and beta refers to the internal diameter to phase thickness ratio. And the number that we use in volatiles is 83, right? And so that means that a 20 meter 1.8 1.0 is the same as a 30 meter 2.5. A 1.4 is the same as a 30 meter. It's basically a 3.2 1.8 film thickness, or a 0.53 millimeter 3 micron film thickness. So we generally keep those the same. Now, the reason we do that is for the gases at the front end of the chromatogram. It's those 6 gases that we're trying to get resolved. Otherwise, you could get away with a thinner film. And also, you'd probably still have the capacity, the ability to run the calibration curve without overloading those analytes. So this at the end here, we're translating our existing methods, but in future webinars, we'll talk about method development from scratch, where we just come up with some compounds and then put together a method and go from there. So that concludes this part of the webinar. And if you have any questions, please let me know. Yeah, thanks, Amy.
Yes, thank you so much, Chris, for joining us today for part 1. And thank you to the listeners for your time today as well. Please check out our website for all of our latest application notes, including US EPA methods using ResTech VMS columns. You can also view past webinars and listen to our podcast. And be sure to visit our online store as well. And you can follow us on social media. Thanks.